In the interest of the time, we'll go ahead and get started. So welcome everyone. My name is Sanjeev Kumar. I will be serving as a moderator for this webinar. This is my pleasure to welcome Dr. Stacey Archfield. She is a research hydrologist with the USGS Water Resources Mission Area in Virginia. She holds a PhD degree from Tufts University, and she is leading a research team that is focused on the hydrologic extreme. Her personal research interest is focused on understanding hydrologic changes for water resources application. And she has previously served as an editor for several journals and currently co-executive editor for the Hydrological Science Journal. So with that, Stacey, this is all for you.
Wonderful. Thank you so much for this invitation. I'm so excited to talk with RUPAC today and others who have joined, because this is a community I think that USGS I think has long been connected to, and I think it's a timely time to talk about non-stationarity and frequency-based streamflow statistics. So thank you for that wonderful introduction. I say that because I just want to make mention this is a topic that I wanted to talk to you about this today, because this is the topic that I think we as an agency are, I guess, thinking about a lot. Is like when we, as you probably know, we are the one of the leaders in developing flood frequency analysis. We do things like develop guidance for how to estimate things like low flow statistics as well. So we provide tools for that, as well as the underlying methodologies. But you may be aware too that there are other federal agencies also working to address these topics. So NOAA is working on Atlas 15, trying to understand how to incorporate non-stationarity into their frequency-based precipitation and IDF curves. The U.S. Army Corps of Engineers is looking for input to update some of their land hydrology guidance documents that they have. You may be aware that FEMA has been looking at this issue with respect to their Future of Flood Risk Data Initiative, their FFRD initiative. And then the Federal Highway Administration in 2016 released updated guidance for highways in the river environment and how to deal with non-stationarity with respect to highway development. So what do you do when you're developing a highway, a culvert, or things like that, and how you deal with non-stationarity? So I just listed off a number of federal agencies that are trying to deal with non-stationarity, and I work in a federal agency as well. And so the question is, how do we at the USGS handle this? How do we provide, as the nation's unbiased resource for information about the land and water, how do we provide information to our federal partners? And then I think more widely, how do we as a community handle this question when we get asked about this in managing water resources? So in that time, hopefully people have had time to join. They've also had time to look at my collaborators and take a look at the people that I work with. This is by no means comprehensive, but these are the people that you'll see pop up on the papers that I've published. I also want to say that this by no means represents the full scope of work going on at the USGS on this topic. This is just kind of some select work that I have been working on this topic. And I just have two pictures represented here, both for floods and then the wastewater effluent side for low flows, because there's a certain low flow statistic that the Environmental Protection Agency uses to decide whether wastewater can be discharged into a stream, whether there's enough water in the stream to have enough dilution for a particular wastewater. Okay, so stationarity, I think most of us on this call know what that means, but let's talk about that if you're someone who's just coming up and learning about that. But stationarity, it is important to think about this, right? So stationarity continues to be a fundamental assumption in water management. So what does that mean? What that means is we assume that the past is a reasonable representation of the future to make decisions about water in particular. That's what we're constraining this to. It's really about making decisions about water. So here's an example of a flood frequency record for annual instantaneous floods for a time period for a stream that's available in Washington, DC. So each blue dot represents it's the highest observed peak annual flow, instantaneous peak for that particular year. So there's one blue dot for each year of available record that we have. And what we would do to find out what the largest, like 100-year flood might be, or a 500-year flood is, we would take these blue dots, fit them to a probability distribution, and then we would pick out that particular probability distribution of interest. And then we would design or make decisions about water based on that particular probability distribution of interest. So that's where we're assuming that the past is going to be a reasonable representation of the future. But really, when we talk about non-stationarity, we ask questions like, what if that assumption is no longer true? What if the past isn't a reasonable representation of the future to make decisions about things like water management or water infrastructure, water allocation? Then what do we do? What is our responsibility as stewards of water research and water kind of information, even in the modeling sense, not just water data? And so we know, right? We've all know that for many, many decades now, we know that non-stationarity exists. In fact, I don't even have to tell you that non-stationarity doesn't exist in time. For many of us involved in ASCE and EWRI, and who are statistical, stochastic hydrologists, we've been dealing with non-stationarity since the very early days, since Furing probably wrote about it. Non-stationarity exists if we have seasonality in our data, right? We don't need to think about non-stationarity as some time varying dependency. Non-stationarity is seasonality. Non-stationarity is a lot of different things. So we kind of already know what non-stationarity is. But we tend to think more in the space right now of non-stationarity being things that just are dependent on time because of climate, because of land cover change, because there's something changing with time. And so in that case, let's look to like what the most current state of the science is telling us about what's going on with climate and changes with time. And that's the most recent document we can point to is this National Climate Assessment. The National Climate Assessment is this congressionally mandated state of the science synthesis that is put out every 4 years. It comes from a legislative act called the Global Change Research Act of 1990. This has to be put out every 4 years, regardless of the presidential administration that is put in place. And this is the 5th assessment now that has been put out. So that for 20 years, we've been putting out assessments. And even since the first assessment in 2000, the year 2000, there's been a chapter on climate and water and how water is going to be affected by climate change. So it's really interesting. In preparation for this talk, I went back and looked through in the year 2000, what was the National Climate Assessment saying about how climate change was going to be affecting water resources. And interestingly, there was some neat stuff. It was mostly focused on snowpack. It was talking about how there's a potential for no regret opportunities. It's worth going back and seeing the evolution of how we've moved forward on talking about water and climate throughout the National Climate Assessment. The chapters have also gotten longer as research has grown. But really, where are we at now in 2023 with the most recent 5th National Climate Assessment? So there's a few key messages that have come out. One is that climate change is going to continue to cause profound changes in the water cycle. Water cycle changes are going to affect all communities with disproportionate impacts for some, and that progress towards adaptation has been uneven. In the scientific sense, when the people who write this chapter or author the entire report, and it's a huge community effort to do this, there's an open call for authors. So it's something to look for when they begin writing. If anybody wants to contribute to this, they're always looking for volunteers for you to be a part of this synthesis effort. But from the scientific sense, it's heavier rainfall combined with changes in land use and other factors is leading to increasing flood damage, and that's likely with high confidence. And then drought impacts are also increasing. So we're seeing what we kind of already know in the research world, right? These kind of like increasing flood damage, and then also drought impacts are also increasing. And then here, and what we're really here to talk about is really what we see in the water kind of infrastructure allocation kind of impact world, is that infrastructure standards and water allocation institutions have been slow to adapt to a changing climate. and that's with high confidence. And efforts continue to be confounded by wet and dry cycles that are driven by natural climate variability, very likely high confidence. And this is really our challenge, right? We live and work in this space. We know why things have been slow to, we know why we, the collective we, the people we work with have been slow to adapt to a changing climate. And we understand the confounding by wet and dry cycles driven by natural climate variability. So this last piece at least resonates deeply with myself. And so now I want to take us back a little bit more so we understand why, you know, non-stationarity is important. We understand why we need to deal with it. And now I kind of want to take us a little bit in time and talk about kind of the crux maybe of this talk, because it's Friday and I kind of want to have like maybe a little bit of a community discussion. Maybe it'll be a little bit of fun. And for those who might not be aware, maybe a little bit newer to the field, it kind of brings back a little flair for the dramatic of a time when I was just finishing my PhD. And there was a paper that came out at the time that I thought was pretty eyebrow raising for me at the time, because it involved a lot of USGS people. So there was this paper that came out in 2008 that was called "Stationarity is Dead, Wither Water Management." And this paper was written by 3 USGS authors. One of them is actually, we're very fortunate to have on the call. At the time, I only knew this person as someone who wrote a textbook that I never thought I'd actually have the opportunity to work with. And now I can call my colleague, Bob Hirsch. But there was Chris Milley, Julio Bentecourt, and Bob Hirsch were USGS employees at the time. But outside of Bob, they weren't necessarily, I would call, people that traveled in the same circle as RUPAC or were traveling in the same circles as my PhD advisor, Rich Vogel. They were kind of like outside of that stochastic statistical hydrology circle outside of Bob. But they wrote this paper, "Stationarity is Dead, Wither Water Management." And it was kind of eyebrow raising to me for some of the quotes that were in there. And so like one of those quotes was, "In view of the magnitude and ubiquity of the hydroclimatic climate, we assert that stationarity is dead and should no longer serve as the central default assumption in water resource risk planning or assessment and planning," which is really bold and assertive statement. And this you can see that this continues to get a lot of attention. So this is 5,100 citations still as of April 24th, 2024. And I gave this talk about this particular slide I showed maybe 6 weeks ago at a different talk. And there was about, I don't know, maybe 200 citations less at that time. So this paper chugs along since 2008. And the other part that to me I really found eyebrow raising was that it was pretty flippant in the way that it talked about the fact that there's in 2008 that we could find an easily replaceable solution. The sentence was, "Non-stationarity hydrologic variables can be modeled stochastically to describe the temporal evolution of their PDFs with estimates of uncertainty." This paper is 2 pages, so you can print it out. It's 1 page. It's a pretty short paper. And it felt a little, coming out of a PhD in environmental statistics, I graduated in 2009. It felt, like I said, it was a different community than mine. And so it was a little bit, it was interesting to wonder like where to go with this as an almost recent PhD graduate. And so then from this kind of came some rebuttals to this commentary. So there was a strong response from the stochastic hydrology community, who kind of, non-stationarity means something very specific to the stochastic hydrology community. And hopefully this kind of resonates with the RUPAC community. I think the people that, you know, the circles that we travel in, right? We kind of think of non-stationarity in a different way, or in a more specific way, I would say not a different way. And so we had these kind of fun titled papers, but very serious papers come out. And these were kind of, the people that wrote these papers are the community of people that I knew, that I traveled in. Also, some of them, most of them were actually USGS employees too. Harry Linz and Tim Cohn were also USGS employees. So there's a paper called "Stationarity Wanted Dead or Alive." Then there was another commentary in 2012, the comment on the announced death of stationarity by Nick Metalis, also a USGS, a statistician employee. And then the last kind of paper that came out that was a play on this was in 2014, called "Modeling and Mitigating Natural Hazards. Stationarity is Immortal." and that was by Alberto Montanari and Demetrios Koutsianis in 2014. And so all of these have different flavors of trying to emphasize the importance of why stationarity plays such a significant role still in the water planning and management community, and why kind of we need to keep those tools in our pockets. All of these papers are very short reads, as well as the stationarity is dead. You're getting my flavor, you're getting my take on this. When I explained this talk last night, I gave it as a practice to my spouse. He called this nerd drama. And I thought this was kind of a funny take on this, but so you're getting my flavor, but I encourage you to read all the papers as a body of work now that we can look back on this. I think it's kind of fun to go back and think about it, because it was kind of an interesting time to be living through these commentaries as they came out. But then essentially, so much of this kind of discussion happened in the scientific community that the original authors plus some additional authors were added in 2015 to kind of put the final kind of nail in the coffin, if you will, of stationarity is dead. And the original authors plus these extra authors came out and kind of, I would say, tempered a little bit of what their original comments said. So they said, we acknowledge the well-founded concern in the community that wholesale abandonment could introduce substantial risk from far from optimal solutions, which is really what some of the criticisms we're talking about. So we really want to avoid gross over-design or catastrophic system failures if we just fully abandon stationarity as dead. And I think most importantly, they understood that some of the bold statements that were made in their original paper about the fact that there was a suitable successor, they clarified that they don't suggest that the suitable successor to stationarity has been found, but they continue to regard finding the suitable successor a major challenge to the community of hydrologists and water resources engineers. So they thankfully acknowledge that this is still a major challenge in the community, and that they're now leaving it to us, I suppose, to do that work. And so kind of the talk today I thought would be kind of fun is that it is the 17th anniversary. It's kind of not a notable anniversary. I don't know what gift you would give. Well, not a gift because it's a death, but the 17th anniversary of stationarity's death. So I think it would be interesting to kind of reflect on some of the USGS efforts to this call to action, but also more because this is a community, because I'm talking to, the community. I think it would be great for us to reflect as a community on this call to action and where we're at. So there's of course still many, I think, reasons why stationarity remains in place. So in 2018, after the kind of 2014 was when kind of there was or 2015 was when we had that kind of last commentary on critiques to the stationarity is dead paper. In 2018, there was a really nice review paper led by Jose Salas talking about techniques for assessing water infrastructure for non-stationarity extremes. So there was a review. So there was some really good things that came out of the stationarity is dead. I think that really motivated our community to start really thinking about, okay, how do we, address this? So one could argue, would this have happened without that paper? We could go, we can talk about that too, have a community discussion about that. But one of the things that really came out of this is, regardless of perceived non-stationarity, a well-defined determinant mechanism must be defined in order to move forward. So you have to know, you can't just extrapolate. Essentially what this paper is saying is you can't just, essentially, even if you see some kind of perceived change that's happening, you can't simply just extrapolate. You need to understand what's driving that change. And there is no standard practices right now. Going through this review that they did, there's really no standard practice for assessing alternative futures, climate over the design life to determine a design flood. And then since then, actually, if you look forward and look at who cited this, there's been a number of really wonderful community papers in 2020. There was a Wasco et al. Paper in 2021. Slater et al. Wrote another paper. And then we have a wonderful paper by Mishra et al. In 2022 in Journal of Hydrologic Engineering. And I cannot capture these papers. I really encourage you to read. They are detailed. They are thoughtful. But most importantly, they are community papers. You can see the level of authorship on these papers to make sure that they captured the full thoughts of the community. I wonder how much more impactful a paper like Stationarity is Dead would have been if it was truly a community paper that really brought together the people at the time who were truly thinking about, the statisticians of the time, the people who ended up writing the rebuttals, that what could have come from that. So, but these papers are really thoughtful community papers that expand on the points raised in Salas et al. And offer their own new insights. And all of them have amazing discussion and conclusion sections, as well as really detailed reviews. And they're very thick and beautifully written as well. But I'll just mention that Wasco et al. Emphasizes the critical importance of practicality, defensibility, and uncertainty of methods when you're applying non-stationarity in practice. Slater et al. Details the current state of science with respect to handling non-stationarity and tools and approaches available. So this is really like when you're really like boots on the ground and you're trying to deal with non-stationarity, how can you look at alternative hypothesis, multiple working hypothesis to attribute trends. And then Mishra et al. Is really a call to action about, we can no longer stand for stationarity. However, it is kind of a stationarity is dead in a way is my reading of it, but it's supported by, number one, the community, and number two, it's detailed, meaningful recommendations for impactful follow-up research that can be kind of taken. There's, I think, 8 recommendations that can be taken and followed up with. So I just wanted to make note of those and draw your attention to those community papers. And it's exciting to see this is the direction that we are moving when we talk about such an important and complicated topic like non-stationarity. Okay, so for us in the federal community, what do we, at least in the USGS, like our guiding light is really this Bulletin 17C. This is the way that the federal community does flood frequency estimation, and what does that say about non-stationarity? So there's a section in here written by, I know personally it's written by Bob Hirsch, that talks about how we deal with non-stationarity. So there's much concern about changes in flood risk associated with climate variability and long-term climate change. In those situations where there is sufficient scientific evidence to facilitate quantification and the impact of climate variability or change in flood risk, this knowledge should be incorporated in flood frequency analysis. But then all such methods need to be thoroughly documented and justified. And this is what, like I said, has been our kind of guiding light at the USGS. And I would argue this is consistent with what the community is arguing, what Salas et al. Has argued, is that we need to figure out where change is happening, how things are changing, what's the direction of change, the magnitude of change, and then what's causing that change, what is the driver of that change. And then once we know those things, what are the methodologies, how do we make adjustments for that change? So I'm just going to give you some smattering, like some just like flavor for the things that we're doing at USGS. Again, like I said, no means comprehensive. These are some recent series of papers that have come out. Now, this is no different than in some ways, no different than a lot of trend work that you've seen, looking at monotonic trends, step trends in the annual peak. And then I have a slide in the lower left here that shows monotonic trends in the annual 7-day low flow. So just, always emphasizing that we're looking not just at floods, but also at low flows, low stream flows. These are all for the same period of record, 1941 to 2015. The flavor here that makes it a little bit different is that in these papers, we look at long-term persistence, we correct for long-term persistence and short-term persistence in the time series. We also look at regulation and isolate gauges out by their degree of regulation, which is usually something that's not done, where typically you do a trend analysis on pristine or gauges that are only impacted by climate. And in these papers, we try to look at regulation and how that might affect trends and their direction and magnitude. And I'm kind of going a little bit out of step here with time, but another line of research that we've tried to explore is Bob Hirsch and I wrote a little commentary that highlighted Gabriele Villarini's work with him and his group on some novel approaches that they've used to try to look at different ways that floods may be changing that are outside of monotonic trends in the annual peaks. And so we wrote a commentary in Nature Climate Change about this. And that drove a different type of analysis that we did, looking at changes in the frequency, duration, and volume and peak of floods. So this is an older paper from 2016, but we continue to use this approach and expand on looking at this peaks over threshold approach in other ways and other research products. So I just wanted to make note of the fact that we have this. So we propose a method that allows for more than one annual peak within each year to be analyzed for trends. And this is a peaks over threshold time series approach. This allows you to look at things like not just the magnitude of one flood per year, but you can look at things like the volume of the event, a duration of a flood event, the peak of the flow event, and then the number of events that might occur per year. This is when you establish a threshold, and then you can do things like categorize floods in that particular way. What we found was that much of the US has not experienced significant change in duration, volume, magnitude, and occurrence of these flood events with few exceptions. And I'll show you results right now. What we did was we individually looked at trends in these particular variables by gauge, and then we gridded the United States into equal-sized grids, and then we lumped these stream gauges into grid sizes and then fit a low S smooth to each one of these to all of the data points from the gauges for all of the floods and all of the gauges that fit within each of these grids. And then we did a statistical significance test there to see if we could see any larger spatial patterns across the United States related to each one of these four components: frequency, duration, peak stream flow, and volume. And you see some patterns come out, but not really. So that's the paper's called like fragmented patterns of change. Then the last thing we did was we did a hierarchical agglomerative clustering on frequency, duration, peak stream flow, and volume to see if we could find any signatures of patterns between all four of them. And so what we did was we were able to find different groupings where we found a group of like a no change group, where all four of these particular signatures of floods were not changing at all across the United States. And that's labeled A in the upper left. And then in the upper right, we found a case for floods where there's increasing frequency in floods, but none of the other particular aspects of floods were changing. Then we found one where all of the aspects of floods, frequency, peak flow, duration, and volume were changing. And then we found a decreasing frequency group where a frequency was decreasing. You could see in Florida in particular, you see that there's a decreasing frequency of floods, but then no other change in the peak flow, duration, and volume. So that was just some outcomes from that, just trying to look at like different dimensions of floods. Another dimension of flooding that we looked that goes beyond looking at annual peaks is looking at has the occurrence of the largest floods changed. So here we wanted to look at whether the largest 10 floods of record have changed. So those are, potentially in a flood record, the 10 largest floods might be the ones that are the most damaging, cause the most problems for life and loss of life and property. Whereas some of these smaller floods, like we'll look at this record here on the far left, they just happen to be the largest flood that was recorded for that particular year, but it might not have actually been a large flood, or it might not have caused any damage. It might not have been problematic. It just happened to be a large flood, and maybe that was just a dry year. So we took 437 stream gauges that we isolated out that are only affected seemingly by climate, not any other types of regulation. And for each of those, we just picked off the top 10 floods. And the problem is when you do that, you can't really do a trend test because you only have 10 data points. So there's not enough data to do some kind of Mann-Kendall or monotonic traditional statistical trend test. And so what we did was we did a probability game, which was kind of fun. We did a 50-year record between 1965 and 2015. And we did this kind of fun, 1966 to 2015. And we did this kind of fun little exercise. And I'm going to show you 3 examples here of end members of this. We split the record down the middle. So we have past 25 years and then what we're calling the recent 25 years. And we look to see, like, are these 10 largest floods, how are they distributed across these 50 years? So in the far left example, we see there's an equal number of large floods in the past 25 years and the recent 25 years. So if you do a count, you'll see there's 5 in the past 25 years and 5 in the recent 25 years. In the middle panel, this North Fork and Barris River near Oblong, Illinois, you'll see that in the past 25 years, there are only 2 floods, but in the recent 25 years, we see there's 8 of the 10 are in the most recent 25 years. So most of the largest floods are occurring in the recent 25 years. But then here in the site in Virginia on the far right, we see that most of the largest floods, like of the 10 largest floods that were observed in the record, we see that they all occurred in the past 25 years, not in the recent 25 years. So okay, so that's kind of neat, right? Like, but the question really is that occurring statistically by chance, or is there actually real evidence that there's something going on here, like in the Illinois site or the Virginia site that we need to look at, that we need to take a look at? And then if there are regional patterns to these changes that on the occurrence of these large floods. And so what we did was we worked out a statistical testing framework, both empirically and analytically, to evaluate for recent changes in any of these large floods. So, so we had one that was obtained by probability theory, and Bob Hirsch actually worked that one out. And then I looked at working this out by exact simulation. And so you can do combinatorics by probability theory, and then exact simulation. You can think about the number of years of record you have, and then you can start doing an experiment of like, think about it like dropping balls into a number of slots. You have 10 balls and you're trying to drop them into 50 slots. And you just want to see what the probability is of those balls falling into the certain number of slots. And so we did that for our 437 gauges, and we plotted the histogram of what actually occurred historically. So if you go back to these 3 pictures, we counted up, we looked at here in this case, like 5 floods occurred for this particular site. So that would have gone in the histogram under 5. It would have gone under a count of 1 here. And we just counted the number of gauges where we saw 5 of the floods occurred in the most recent 25 years, or where 10 of the floods occurred in the most recent 25 years. And we know that if things happen by chance, that curve for those 435 gauges should follow this expected curve. And then within these confidence intervals that we were able to obtain by using the simulation process. And when we actually plot up what we would expect by chance versus what we observed in the historical data, we find actually that there have not been, for the United States, the occurrence of the 10 largest, and then we did this for the 2 largest floods. We could do this for any number of largest floods. The most recent 25 years are not different than what is expected. We actually also did this. You could do this for any number of recent years. We also did this for the most recent 10 years. You could play any number of probability games with this work. I will mention this paper, Collins, Hodgkins, Archfield, Hirsch, in Water Resources Research. The primary author, Matt Collins, looked at the seasonality of large floods, and Hodgkins looked at the regional trends in large floods. So this particular aspect was unique to myself and then to Bob. So I just wanted to acknowledge the contributions of each of the authors. So I'm not talking about Collins or Hodgkins here. And then the last thing we did was we just wanted to look at, okay, so that's fine. We know these things expect by chance, but if we plotted what was going on at the tails, where there was kind of like less floods in the more recent period than was expected, or more floods in the recent period than expected, did we see any regional patterns, even though we knew they were kind of expected by chance? Do we see any regional patterns? And maybe it's speculative that, in the central US, there were most of the large floods that were here on the tails were experienced in the central, maybe in the Midwest, and then there might be some less number of the largest floods observed in the more recent 25-year period. There were less of them observed in the southeastern US than in the past 25 years. Okay, so then I want to talk about some work that I was not directly involved in, but I think that people might find useful. So that was more on trend detection. I wanted to talk a little bit about attribution. My colleague Karen Breiberg led an effort that involved 20 or 25 or so USGS employees. As you may know, we have USGS staff based in every state in the United States. So they have really like boots on the ground, I would say, knowledge of what goes on with stream gauges and the drivers of floods and climatology that might be happening there. And Karen led an effort to attribute trends using a multiple working hypothesis framework for every stream gauge in the United States that had a statistically significant trend. If you remember that body of work that I showed you from 2019 and 2020, those monotonic and step change trends, every one of those gauges that had a statistically significant trend, a team of people went in and actually looked gauge by gauge to see if they could make an attribution of what was causing that trend. And that data set is actually available for anyone to download. And that citation is here. And this is this is what it looks like when you pull it up. It's a CSV file, and I'm just going to show you. It has the site ID, the stream gauge number with the state that it's located in. It has some information about the trend. And then it has a primary attribution, a secondary attribution, if possible, for what caused that trend, some notes, some assessment of the level of evidence, and then some notes about that. So for example, this trend in Connecticut that was observed is probably likely due to short-term precipitation. There's a medium evidence for that to be the case, and then there were no notes. And then you can just go down and see. I think this is an incredible body of research that really leverages the expertise that we have at the USGS for the knowledge, the site-by-site knowledge that we have for people who are located in our state offices who are, just leveraging that wealth of. I also want to talk about a national analysis we have that we used to attribute effects of imperviousness. This is the first study to apply a panel regression design to estimate the causal effects of impervious cover on floods. And what we were able to do with this is, for the first time, instead of using site-by-site analysis, field analysis, we were able to isolate the effects of changes to impervious cover from other confounding influences. Panel regression is commonly used more in econometrics. I think it's becoming much more common now in the literature. In 2020, it wasn't so much. But what we were able to do is basically take this large data set, despite the fact that there were positive and negative flood trends. We were able to put this into a panel regression framework. And what we found is that we were able to estimate that annual floods increase about 3.3% on average for each percentage point increase in impervious basin cover. And this is true even at sites that had decreasing trends or no observed trends in floods. So even when there were decreasing trends, what the panel tells us is that floods would have still been larger than they would have been in the absence of impervious surfaces. And that's one of the strengths of panel regression, is that you're able to kind of isolate these effects and get a good estimate on your regression coefficient, a more robust estimate on your regression coefficient than you would if you use multiple linear regression, where you have a less reliable estimate. So that's kind of a plug for panel regression, and you can read more about that in this paper. The other thing I want to note is the lead author on this paper worked with me and colleagues at the USGS, Annalise Bloom, when she was a graduate research fellow, finishing her PhD with Richard Vogel, and working with me as well on this graduate research fellow program as a NSF GRIP fellow, which allows you to work with a federal government employee while you're also funded in this NSF as part of this NSF project. And Annalise is now the Deputy Assistant Secretary for Water and Science at the Department of the Interior. She's actually like so many layers of management above me. And she works at the executive government level. And I just want to just say, it's like just a little like side note, that it's really exciting and rewarding to know that, first of all, like that we have amazing people, you know, that can rise to that level of government with this type of, I would say, like acumen for science, to know that they are representing us at the executive level. And I think it's also a reminder that you never know who you work with, right? And where they end up. And so I think it's always important. This is the advice that my PhD advisor gave me, was that you always treat your students like colleagues, because they will be your colleagues someday. And I think it is always good advice for us to always remember that, that we are all colleagues, no matter what stage of career we work at with each other. And so I just wanted to just to say that, yeah, that Annalise is amazing, and it's wonderful to have her representing us at the executive level. So lastly, before I get back into non-science and we're going to wrap up, is I just wanted to talk about low flows a little bit. Another piece of work that Annalise worked on with myself and USGS colleagues. So this is talking about adjustment for change in low flow extremes. So here, as I alluded to, this is about how do we adjust for the 7Q10. So this is a minimum mean 7-day flow that occurs on average once every 10 years. So this statistic is used in water management specifically by the Environmental Protection Agency. And if you Google EPA 7Q10, you will find the documentation for this. It's enshrined in their federal regulations. It's a standard for dilution of wastewater effluent. So if a stream is below the 7Q10, the minimum mean 7-day flow that occurs once on average every 10 years, you cannot discharge wastewater effluent in that river. So that's a pretty significant regulation. And EPA funded USGS to understand if the 7Q10 is changing, increasing, or decreasing, what should they do? What should they do with that non-stationarity? And what is a simple rule that perhaps we could come up with to update to current conditions? They weren't interested necessarily in future projections, but should they be updating at least to current conditions? And so that's what I just said here. If the annual 7-day minimum has changed, should one still use the entire historical period or perhaps only a more recent period? And that's kind of a common question we have in statistics we struggle with, right? If we know something's changed, should we just use the period under which we know that the change has occurred, or should we use the full period? If we use the full period, we're gaining, perhaps we are using, more record is always where we've been trained to think is better. But if we use shorter record, maybe we're capturing that trend better. So we just have to think about what's the best way to proceed. So what we did was a series of idealized experiments where we generated the truth. We knew what the 7Q10 was. We made an assumption about its moments, its distribution, and we knew the truth. And then we did a series of experiments to test whether using the full record was better or whether using a subset of 10 years, shown here in the orange, whether a subset of 30 years, or whether a subset of the most recent 50 years. So was it better to use the most recent 10 years, the most recent 30 years, the most recent 50 years? And what we did was, knowing the truth, we induced stronger and stronger trends on that record, negative and positive trends on that record, on that truth, to see would we get a different result. And what we see is, so in this case, the improvement factor is basically anything below 1 that's in the gray would mean that you would want to use the full record. Anything in the white above would mean you would want to use the subset, anything that falls above. And then the colors are the different subsets. So you could see for the orange, the lowest line, you would really not want to ever use a 10-year subset to estimate the 7Q10 unless you had really, really strong trend magnitudes. It's a standardized magnitude. And then you could see as you move up more forward, you would tend to favor more and more a subsetting of 50 years and 30 years as you move forward, as you move up. What we ultimately decided is a set of rules as we looked at the trade-offs and evaluated the trade-offs is that we also tested what p-value you would want to use to not just know the trend, like in this case, we knew what trend we induced, but the detection of the trend. So we also tested different things like standard deviations as well. And so what we found is that we were able to hand off through these idealized experiments a simple rule-based approach that we were able to provide in the paper, where you would apply a Mann-Kendall trend test to a series of low flows. If the trend was significant at the 0.1 level, so your p-value was less than 0.1, then you would select the most recent 30 years of record to estimate your 7Q10, and you could use any method you wanted to, whatever distribution choice you chose. But if you didn't find significance at the 0.01 level, then you would use the whole record and then estimate the 7Q10. So these were kind of, we felt like simple, we thought this was a nice, elegant, like simple rule-based approach, at least to update to current conditions. And then lastly, I'll just take a minute to describe. So we talked a lot about trend detection. We talked some about trend adjustment. We talked some about trend, so detection, attribution, adjustment. And I just wanted to add a paper in here about when to adjust. And so there's a paper that just recently came out with my colleagues at NC State looking at when do you make that adjustment, right? And so this is a hypothesis-based framework that's been developed, so oftentimes we look at observed changes in just the instantaneous annual maximum flood. And we use that assumption, and we're really just looking at, right, the change in the mean instantaneous flood. And if we see a change in that, we make some assumption that the flood quantiles have changed. The 100-year flood has changed, the 50-year flood has changed, 25-year flood has changed. We make that assumption. But this hypothesis testing framework is actually a more formalized way that kind of supersedes the testing of the annual instantaneous maximum flood that takes into account all the moments, not just the change in the annual maximum flood, but it thinks about changes in the mean, standard deviation, and the skew. So it proposes a hypothesis testing framework to help answer the question of the changes in the flood quantiles, and not just the assumption, oh, if we see a change in the annual maximum flood, then maybe we should make a change in our design quantile flood. And one of the interesting conclusions of this paper is that statistically significant changes in design flood quantiles were observed even without a statistically significant trend in the annual maximum flood series. And then we also saw statistically significant trends did not necessarily exhibit, and we also saw the reverse. I'll just summarize it in that way. Okay, so I'm talking again specifically just about, very much like a flavor of USGS research, and now we're going to kind of switch back to where I want to talk a little bit about the community and where to go from here. So I've given you just little data points. I just want to be very clear. This is just if you sampled from another sample, from the sample space of USGS employees, you would get another set of research that we're doing. And if you sampled from the larger sample space of people doing non-stationary work in the US and then out to the globe, you would get a whole different kind of talk, right? So I want to bring it back out a little bit now and finish with the last few slides that I have. One of the things that I was really excited to talk to you about today is that we are, there's been, I think, as we move forward in time, some loss of memory of processes. Now I'm talking human memory, not scientific memory of processes, of kind of how we move from research to operations in flood frequency analysis, how we've done that, how we have proceeded there. And I think it would be interesting, hopefully to you, certainly to me, to the larger community, as I've described this progression that we've seen, particularly on topic of non-stationarity, to look at an example of how we moved from Bulletin 17B in 1982. We're talking now 40 years it took to go from there to Bulletin 17C in 2019. And so that movement I kind of traced, and I want to acknowledge Nancy Barth and Jared Smith at USGS for pointing out some of the papers that really contributed to that movement. But it started back in 1997. First, it started with Bulletin 17B, gave breadcrumbs, not even breadcrumbs, whole sandwiches on what are the things that need to be fixed and addressed in an update, the next update. And then and I don't even represent all the papers here. I'm just giving you, again, a flavor of the papers. 1997, we had some papers in 2001. These are all methodologies that ended up moving into the 2019 update to our nation's, way that we do flood frequency analysis now in the United States. Then we had a series of papers in 2007, two in 2002, not in 2008, 2009. We had a paper in 2011. 2013, some are methodological, some are statements about why we need to update, but they're all moving us all the way forward until basically we get to a place where we decide, okay, it is time to update from 1982 to 2019, and there was at some point a decision amongst the community. 17C was led by the Army Corps of Engineers as the lead author, USGS, published by USGS Publication Series, but there were many people, academia, industry, the federal space that contributed. It was truly a community effort that brought this to bear, and probably the reason why we all buy into it, we all follow it. And so I guess that leads me to my concluding thoughts. So in practice, there are still many reasons why stationarity remains the default assumption. In other words, I think stationarity is dead, but 17 years later, we still cannot bury it. It's out. I don't know if it's a zombie. I don't know what analogy we want to use, but we can't bury it yet. There are statistics that are entrained in federal and state regulations, and they require a community effort and they require collaboration to make changes in methodologies. I think we have these guiding lights, these beautiful community papers that are only just a few years old that can help us, but they're still pretty young, and there's going to be time for them to take hold and do the work required that they call us to action on. I think I just want to say that the USGS has a mission to provide, objective and impartial science. Historically, we've played a critical role in how best to estimate these statistics. And then we also have provided the tools and training that come along with that. Out of Bulletin 17C came Peak FQ and other tools and training that we provide as a result of that. So I guess the question, I'm curious about is like, when and how will we know our grieving period for stationarity is over? So we've accepted it's died, but when will we know we can collectively agree that a suitable successor has been found? When do we move from research to operations? How will we assess that? It seems like it's a nice story I've wrapped up, showing the papers and how we move from Bulletin 17B to C, but how will we know that for non-stationarity? It seems a bit murky to me now. So it took 40 years to get from 17B to 17C. And there feels like this intense pressure. I don't know if you feel it, I feel it. It's only been 6 years from 17C, but it feels like we are being called to a 17D, particularly on this topic. And so I guess for me, this tension exists. How do we move forward at this pace that acknowledges non-stationarity, but honors these complexities? Do you have these struggles? What is our community journey on this research to operations pipeline for this topic? And how do we make sure other people aren't connecting to this pipeline that aren't being responsible about it? I guess is another question I have. Yeah. So I think I'm going to end there. I hope this was useful of your time. Yeah, thank you.
Thank you, Stacey. This was an exhaustive set of work.
So hopefully you're not exhausted.
And thank you to USGS. Like I started my graduate work with the USGS data set. So
wonderful.
So I guess we'll open the floor for question and answer. So anybody want to ask the question, just either raise the hand or unmute yourself and you can ask.
Let me see in the chat too. I did just want to plug that we have a new version of the statistical methods for water resources. If people are not aware of it, it's out and you can order it. It's very inexpensive if anybody is unaware of that. So I'll just leave that slide up. Thank you. I'm going to see if I can open the chat too.
Okay, so while waiting for question from the audience, yeah, you can raise your hand or you can unmute yourself. Let me get. Yeah, go ahead, Ashok.
Yeah, very nice presentation, Stacey. So it was great. So I have a quick question. So how do the stakeholders, when you talk about the non-stationary to the stakeholders who are making bridges or making dams or any infrastructure, so how serious they are about the non-stationarity?
Yeah, I think that they really, I think they want answers. Like, I think that there are people, I think we have done a very good job at convincing them that we need. I think there is no doubt that they believe that this is happening. They see it. Particularly, I work particularly with in the highway space. I've done a lot of work there, and I think even I sit on the technical mapping advisory committee, like with FEMA, and I think that there's no doubt that people want to move forward on these things, but because it matters to life, like life and loss of property, but it's so it's so unsatisfying. I feel so, it's hard as a scientist, as a researcher, to not be able to then just say, we have the answer for you. I think that's where I, you know, it's just a very difficult thing. Yeah, I don't know how you feel, so it's almost like an emotional problem, and then more than I don't know, yeah.
Thank you, Stacey. It's always a challenging to convince them. My experience has been a little bit challenging.
Yeah.
Typically in the South Carolina, you know, they got back to back like 100 years of flooding because of the hurricanes. So they are saying we are seeing so frequent in last 10 years. So they say that, you know, we need to be serious about it, but we don't have resource to improve our infrastructure or something.
Yeah.
Thank you.
Yeah, thank you.
Yeah.
Thank you in the community. Yeah, truly. Yeah.
Paul, you have your hand raised. Do you want to go ahead and ask your question?
Sure, Stacey. Very, very nice talk. So much content. It's a joy to hear. So I just want to mention something about, let's say, somewhere in the middle of your talk, you talked about doing a permutation test, looking at the last 50 years of annual data and randomly permuting those 50 years and seeing whether the first half is different from the second half. Okay, so you know, it's a nice idea.
Recording
And
नहीं हो रही है.
pardon me?
Oh, no, I think someone's not on mute. Oh,
Recording
Okay.
पता नहीं कब.
Yeah, okay, so
okay,
I'll
there it goes.
continue.
Yep.
Right, okay. So so permuting is a good idea, but instead of doing the so partition two halves, you could do something that is a little bit more sensitive. For example, you can do a test for trend and still use a permutation idea, and you'd gain considerable power in your testing procedure, and you'd have the same validity, and it wouldn't just depend on a dichotomy between the two halves. So that's one comment.
Mhm.
And the other is with regard, say, with the same type of thing. So you have multiple sites at which you see some at no change, some with change, some negative change. And when you're looking at multiple sites, you can ask them question, well, suppose things were happening randomly. And when I look at multiple sites, I might observe some purely by chance that look like that pass the test on an individual basis. So
Yes.
somehow I have to account for the fact that I'm using the same test at multiple sites. So you might want to look at things like family-wise error rates and things like that control the error rate, the number of errors you're allowed to make over multiple sites. And that's not, of course, it's very complicated because there's a lot of geographic autocorrelation. So you have multiple sites close together, then you expect perhaps the trends to be similar. Anyhow, these are my comments.
Thank you so much for those comments. So the idea of the permutation, but test for trends, I think that's really interesting. I think what I'm hearing in your other comment about the field significance, if I'm summarizing it correctly, this idea that that there's a possibility of things in spatially located that could be coming up as significant, even though it just happens to be by chance that they're just co-located. And I'm not testing for that. We did do that. We did test for field significance in one of the papers, but not in the paper that you're referring to. We didn't look at that, and that's a really interesting idea. And field significance is much more common in climate. It's much less common in the hydrologic literature. I think that's a very interesting idea to understand how that might have affected our results. So if I've captured that comment, maybe field significance wasn't what you were getting, but either way.
Well, what it was very just apart from the geographic autocorrelation part there, I was just commenting that you might expect by chance, if you have many sites, that some of them will look like they're like will pass any test for an individual site.
Mhm.
So just accounting for the fact that you're doing the test over multiple sites.
Yeah, got you. Thank you very much for those comments. They're great.
Okay, so is there, yeah, I see some of the question on the chart too. So we are reaching top of the hour. So in the interest of the time, like let's thank Stacey one more time. And yeah, you can I guess like people can reach out to you directly, and almost everything is published. So there are some interest in if you can share your slides with us, then yeah, our chair can share the slide with all of us or whoever is interested, and people can reach out to you too if they have more questions.
Sure. I think this is recorded for anybody who is wondering too. I think this will be posted, right? Yeah, somewhere. So, yeah.
Okay.
Thank you so much for this opportunity. Thank you.
Thank you.
Thank you.